All right, so today we're going to dive deep into something pretty cool, the invisible architecture that basically runs our entire wireless world. It's called the LTE Frame Structure. You can think of it as the ultimate rulebook, the thing that keeps all our calls, texts, and videos from turning into total chaos. So let's pull back the curtain and see how this thing really works. I mean, have you ever stopped to think about it? It's kind of wild. Every single time you stream a video or just send a quick text, you're out there competing for airtime with literally thousands of other devices all around you. So how on earth does your phone know exactly when it's supposed to talk and, just as importantly, when it's supposed to listen? Well, the answer is this really elegant system, the LTE frame structure. It's like a traffic grid for our data. It's this super organized method that slices up both time and frequency into these tiny, perfectly managed pieces. This makes sure that everybody gets their turn on the network without causing a massive digital traffic jam. Okay, so to really get how the system works, we first need to zoom way in and take a look at the fundamental building blocks. These are the basic components that you'll find in all LTE signals, no matter how they end up being put together. It all starts here, with this one number. You see, in the world of LTE, the biggest chunk of time is called a radio frame, and it lasts for exactly 10 milliseconds. Every single thing that happens is timed and synced up inside this constantly repeating 10-millisecond window. And here's where it gets really neat. It's this perfect nested hierarchy. That main 10-millisecond frame, it gets broken down into 10 smaller subframes, and each of those is exactly 1 millisecond long. Then, if you zoom in even further, each of those subframes splits perfectly into 2 slots, each lasting just half a millisecond. And believe it or not, we can go even smaller. Inside every one of those half-millisecond slots, you'll find 7 incredibly tiny units of time called OFDM symbols. Now, OFDM might sound super technical, but it's really just a clever way of sending data across a bunch of small signals all at once to make the connection more stable. This is the level where the actual bits and bytes of your video or your message get physically stamped onto the radio wave. So, we've got the time dimension all sorted out, right? But what about frequency? Well, that's where the resource block comes into play. You can think of this as the smallest possible piece of radio real estate that the network can actually assign to you. It's a little grid, 12 subcarriers wide in frequency and 1 slot long in time. So here's the key takeaway. When your phone gets data, what's really happening is the network is assigning it a certain number of these resource blocks. Okay, so now we've got our building blocks, right? We have our slots, our subframes, and our resource blocks. Now we can start looking at the 2 totally different ways LTE can arrange these blocks to handle that two-way street of communication, all your downloads and all your uploads. And this slide just illustrates the 2 core philosophies perfectly. On one hand, you've got FDD. Think of it like a dedicated 2-lane superhighway. Downloads get their own lane, uploads get their own lane, and traffic is just flowing nonstop in both directions all at the same time. But then you have TDD. This is more like a clever single-lane bridge. It only uses 1 lane, but there's a traffic controller who's rapidly switching the direction, first letting all the download traffic through, and then flipping it to let all the upload traffic through. So let's drill down into FDD for a second. That's our 2-lane highway. Because it has those totally separate frequency lanes, your uploads and downloads can happen at the exact same moment. This makes scheduling everything pretty straightforward for the network. And it means you get very, very low latency, because you never have to wait for the direction of traffic to change. It's just continuous and super efficient. Now let's go back to TDD. For that single-lane bridge to work, it needs that traffic controller, right? It needs a specific moment in time to safely switch from downloads to uploads. In LTE, that controller is a really important little thing called the special subframe. Honestly, without it, the download and upload signals would just crash right into each other. And this special subframe is itself split into 3 little parts. First up is the WPTS, which is basically the last possible chance to squeeze in some downlink data before the switch happens. Next, and this is absolutely critical, comes the guard period, or GP. This is a brief moment of total radio silence which prevents a collision. And finally, you get the UP-PTS, which opens the gate for the very first bits of uplink data to be sent out from your phone. So you might be asking, why go through all this extra complexity? Well, here is TDD's absolute killer feature. Flexibility. And this is so important for how we use our phones today. I mean, think about it. Most of the time, we're just streaming videos or browsing websites, which means we download way, way more data than we upload. TDD can adapt to that on the fly by giving more time slots to downloads. But say you're at a concert and everyone is live streaming video. The network can instantly flip that ratio to prioritize all of those uploads. It's totally dynamic. So what we have is FDD's simple, low-latency two-lane highway going up against TDD's flexible, super adaptable single-lane bridge. Let's bring it all together now for a final head-to-head comparison. This table just lays it all out perfectly. FDD needs what's called paired spectrum, two separate bands of frequencies. TDD, on the other hand, can work with a single unpaired band. With FDD, uploads and downloads are simultaneous. With TDD, they're time-shared. And because of that, TDD needs that special subframe we talked about, which does make it a bit more complex. But here's the big trade-off. FDD has pretty low flexibility, whereas for TDD, that high flexibility is its greatest strength. And at the end of the day, this is really the whole point. FDD and TDD, they're just two different but equally brilliant ways to solve the exact same problem. How do you organize the airwaves to support our nonstop need for two-way communication? And how do you do it efficiently without everything interfering with everything else? So as we look ahead to 5G and whatever comes next, where our data demands are only going to get crazier and more unpredictable, it leaves us with a really fascinating question to think about. Will the elegant simplicity of FDD's two-lane highway win out in the end? Or is the clever shape-shifting flexibility of TDD's single-lane bridge the true path forward for our data-hungry future? Thanks for joining me on this